All right, let's kick this off with a classic scenario. Imagine this. Your service is, by all accounts, perfectly healthy. Every server is just humming along, all your dashboards are a beautiful sea of green. But thousands, maybe tens of thousands of your users are staring at a blank screen. They can't connect. You're in the middle of a massive outage and your own systems are completely silent. That right there, that's the invisible error, and it is one of the trickiest problems in systems design. And today, we're going to solve it.
Oh, exactly. A server error? A 500? That's noisy. Your logs just explode, alarms are firing off, your on-call engineer gets paged in the middle of the night, you know something is wrong. But a client-side failure? That's just silence. It really is a ghost in the machine. You're losing users, you're losing revenue, you're losing trust, and you have absolutely no signal, no data telling you why. That silence, that's what keeps engineers up at night.
So here's our game plan for hunting down this ghost. First, we're going to define this invisible error and really understand its anatomy. Then we'll do a quick flyby of monitoring fundamentals. The classic push versus pull models. From there, we'll look at some pretty scary ways the internet itself can break. Then we'll evolve a solution, starting with a simple prober and moving to a way more sophisticated agent-based system. And finally, we'll tackle what is arguably the most critical part, implementation and making sure we nail user privacy.
Right, so Section 1, the invisible error. The most common trap people fall into is thinking, oh, I'll just watch my traffic graphs. But that's kind of like trying to detect a power outage in a single neighborhood by looking at the national power grid. A little dip in traffic could just be the normal ebb and flow of a Tuesday afternoon, which would be a false positive. Or worse, a massive outage for all your users in, say, Australia might just be a tiny blip you completely miss, a super dangerous false negative.
And the crazy thing is, the causes for these errors are all happening out there in that wild, unpredictable space between the user's device and your front door. It could be their local DNS, which is basically the internet's phone book, failing to find your address. It could be a BGP routing failure. Think of that as the internet's postal service, sending traffic down a dead-end street on the other side of the planet. Or it could be a CDN or some other third-party service just having a bad day. None of this stuff will ever touch your server logs.
So before we can even begin to architect a solution, we have to go back to first principles. Section 2 is our monitoring 101. We really need to decide on the fundamental way our system is going to gather data because this one choice is going to dictate pretty much everything that follows.
And it always starts with metrics. You know the old saying, you can't fix what you can't measure? Metrics are simply our objective data points, things like CPU load or network latency, or in our case, connectivity error rates. They're the raw signals that let us actually quantify the health of our system.
Okay, so how do we actually get those metrics? Well, there are two canonical models. In a pull strategy, your central monitoring system actively reaches out and, scrapes an endpoint on each server to get the latest data. Just think of it as polling. In a push strategy, each server is responsible for actively sending its own metrics to the monitoring system. Now, the key thing to remember here, and this is super important, is that the perspective is always from the monitoring system. Is it pulling data in, or is data being pushed to it? And believe me, this distinction is going to become absolutely crucial when the client can't even reach us in the first place.
All right, so up to now, we've been talking about individual client connection issues. But what happens when the problem isn't just one client or one ISP, but a fundamental piece of the internet itself just breaks? Let's dig into some real-world, large-scale, invisible outages.
This is a perfect and kind of terrifying example. So BGP, the Border Gateway Protocol, is essentially the routing system for the entire internet. Back on November 12, 2018, a provider mistakenly announced to the world that it had the best path to all of Google's IP addresses. This is called a BGP leak, and it essentially hijacked traffic. It was telling a huge portion of the internet, hey, forget the normal route, send all your Google traffic to me instead. For a full 74 minutes, Google's services were 100% healthy, but for millions of users, their traffic was just being routed to a black hole.
And these are not just some freak isolated incidents. In April 2021, another autonomous system, which is basically a big network like an ISP or a cloud provider, mistakenly announced over 30,000 BGP prefixes. And the result? A 13-fold spike in traffic to their network, causing widespread outages. This just goes to show you the scale of these invisible problems. They are massive, they're unpredictable, and they're completely external to your service.
So how in the world do we build a system to detect this kind of thing? Okay, let's move to our architecture and actually see how this evolves, starting with the most intuitive but, as we'll see, ultimately flawed first attempt.
The first idea you'd probably have, and it's a logical one, is what's called a prober. The idea is simple. We'll set up servers in data centers all over the world, and all they do, day in and day out, is send periodic requests to our service to check for availability. They're basically acting like synthetic clients, giving us these vantage points across the globe.
But here's where this model completely breaks down: the scale of the modern internet. As of 2021, there were over 100,000 unique autonomous systems out there, those distinct networks we talked about. To get anything close to real coverage, you need a prober in every single one of them, from the giant ISPs to tiny regional networks. It's just economically and logistically impossible. Your coverage will always be a tiny, tiny fraction of the real world, leaving these massive blind spots.
So, this leads us to the crucial architectural pivot. If we can't bring thousands of probers to our users, what if we could bring the prober to the user? And this is the breakthrough. We embed a tiny piece of code, an agent, directly into our own client application. Now, when that client fails to reach our main service, the agent activates and sends a failure report to a completely separate, totally independent collector service. And just like that, in an instant, we've turned our entire user base into a globally distributed network of millions of probers.
And listen, that word independent is not just a nice to have, it is absolutely critical. This brings us to a really important concept in reliability engineering, the blast radius. Think about it. If your main service is down because, say, your primary cloud provider is having a massive outage, what's the last thing you want? You definitely don't want your monitoring collector to also be down because, oops, it's running in the very same cloud provider. The collector must, and I mean must, be outside the blast radius of your primary service. That way, it's guaranteed to be available precisely when everything else is, well, on fire.
All right, so we've got our architecture, agents and collectors. Now let's get into the nitty-gritty implementation details. In this final section, we'll see how this builds into a real system, and most importantly, we'll cover how to build it ethically, with user privacy as a non-negotiable top-tier requirement.
So you might be wondering, how does the agent even know where to send these reports? It's actually a pretty clever mechanism. The agent just lies dormant until the client makes a successful request to the main service. The service then replies with a custom HTTP header that essentially says, "Okay, agent, you're now activated. If you see a failure from now on, I want you to send the report to this specific collector address."
And this is exactly how we ensure the collector itself stays available. We have to assume that the same things that break connectivity to our main service could also break connectivity to our collector. So we intentionally place collectors in different failure domains. If the fault is DNS related, well, the collector is on a completely different domain. If our primary autonomous system gets hijacked, the collector is in a different AS. If our CDN goes down, the collector doesn't use that CDN, or maybe any CDN at all. You have to design for failure at every single layer of the stack.
Now, let's talk about the single most important constraint in this entire system: user privacy. Look, this monitoring capability is incredibly powerful, but with that power comes immense responsibility. The absolute unshakable guiding rule must be to collect the absolute minimum amount of information necessary to diagnose the problem, and nothing more. And it must only be done with explicit user consent. Period.
So what does that mean in practice? Well, it means we absolutely cannot collect traceroute data, which can easily be used to pinpoint a user's geographic location. We can't collect their specific DNS resolver details because that can also leak location info. No detailed round-trip time or packet loss information. The goal here is to get an aggregate signal that says, hey, a group of users from this general network region couldn't connect, not this specific user at this specific IP address couldn't connect. That's the line we can't cross.
So we'll leave you with this final thought, which really gets to the heart of why all of this matters. Your dashboards are all green, your servers are healthy, everything looks perfect. But a significant portion of your users are seeing a broken page. Now, with a traditional, purely server-side monitoring system, you might not know for hours, not until the complaints start rolling in on social media. With this design, you could know in minutes. So the question is, how long would it take you to find out?